So in this unit, the integration unit, we were introduced to the concept of integration, which is basically just the opposite of differentiation. I just want to let you know that I've skipped a big topic, Riemann sums. When I tried to fit it into the original video, I either had to rush or have the video be like half an hour long. So I made the videos separate. This allowed me to take my time a bit more while keeping the videos watchable. Let's start off by talking about slope fields. If you're given a differential equation and you graph the slope at each point, you get this conglomeration of lines. You can draw a shape through them, and this is one of these solutions. Notice that you can also draw another line through them, and this is another one of the solutions. This is important because it shows that a differential equation has infinitely many solutions. So if you're asked to draw the slope field of a differential equation, you might be given a point that the solution has to pass through. Like for example, you might be given that it has to pass through 0, 2, or you might be asked for one of the many solutions. Now let's talk about the indefinite integral. An integral is basically the opposite of the derivative. So since the derivative of x squared is 2x, the integral of 2x is x squared. Now, if you remember the rules for the derivatives, just know that the opposite applies for integrals. For example, the integral of 0 is just c, and the integral of a constant is kx plus c. We still have the sum and difference rules, which remember if you're integrating the sums of two functions, that's just going to be the integrals of each of the individual sums. I can add these, or if I'm subtracting them, I can subtract their respective integrals. And then for the opposite of the power rule, instead of multiplying by the exponent and subtracting 1, we're going to add 1 to the exponent and then divide by the new exponent. For trig integrals, you have to recognize that this is the derivative of some trig function, then just identify which one it is. For example, this is going to be cosine of x, this is going to be sine of x, this is going to be tangent of x, this is cotangent of x, this is secant of x, and this is cosecant of x. And now what I'm going to do is I'm going to add a plus c to all of these. This plus c thing that's at the end of every integral just means that there could be any constant at the end of the integral. You don't know exactly what it is, because if you took the derivative of this of any of these, you just get back to here, and the plus c would just go away. So because the derivative of a constant is just 0, so we add the plus c to just show that there could be a constant that we don't know about, and you put it at the end of every indefinite integral. Here are some more things that you might want to remember. And you might use indefinite integrals when solving differential equations. A differential equation is just when you're given dy dx in terms of y or x. For example, you might be given the equation dy dx is equal to 2x and the initial condition f of 2 equals 5 and asked to find the equation. So what you'd do is you'd first integrate both sides to get rid of the dy dx, and you'd get y is equal to, so I'm going to add 1 to the exponent and then divide, and that gets me x squared. I'm going to add the plus c. To find out what the c is, we're going to use this initial condition. So I have the function y equals x squared plus c. I'm going to plug 2 comma 5 into my equation and see what the c value is. So we'll get 5 equals 2 squared plus c, and then c equals 1. So our final answer is y equals x squared plus 1. Took the integral, and then we used our initial condition to find the value of c. Notice that if we took the derivative of this, we'd go right back to 2x, and then this plus 1 just disappears. The reason that it disappears, the fact that it disappears is why we use plus c when we're going the other way. Now we're going to talk about a way to solve some indefinite integrals known as u-substitution. This is used when you have a function and the derivative of that function in the integral. For example, in this function, we have the function x squared, and we have its derivative 2x. Now, if there was a coefficient other than 2, the method will still work, but there's an extra step. We don't have to worry about that right now, however. So the first step here is to set the function that we know the derivative of equal to the variable u. In this case, we'll say that u equals x squared, since we know the derivative of x squared, and it's here in our expression. So taking the derivative of both sides, I get du dx equals 2x. Let's do something interesting now and multiply both sides by dx. This gives du is equal to 2x dx. In the original integral, we have a 2x dx, so we can replace the 2x dx with du. And then the e to the x squared, since u is equal to x squared, this is just e to the u. Therefore, we now have the integral of e to the u, and the 2x dx got replaced by du. This is something we can solve, and it is equal to e to the u plus c. And in the beginning, we set u is equal to x squared, so now I need to replace the x squared in for this u, so giving me my final answer of e to the x squared plus c. And I just want to draw your attention to this type of problem, where you're still going to use u-substitution, but it's going to be in a slightly different way. The x plus 5 here is a problem. We only want one thing under the square root. Therefore, I'll set u equals x plus 5. Taking the derivative of both sides gives du equals dx. And here's where the trick comes in. Since u is equal to x minus 5, or u is equal to x plus 5, x is equal to u minus 5. And since I have an x minus 3 here, I'll write this in terms of u, giving me, so x minus 3 is equal to x minus 5, or u minus 5 minus 3, which equals u minus 8. And now I can rewrite this integral as the integral of u minus 8 times, so we had the u is equal to x plus 5, so this is just the square root of u. And then dx is equal to du, so I'll write the du here. Since there's only one thing under the square root, I can distribute it. So I'll get u to the 3/2 minus 8u to the 1/2. And then I can integrate this by adding 1 to the exponent and dividing. So if I do that, I'll get 2u to the 5/2 over 5 minus 16u to the 3/2 over 3 plus c. And then your next step, I'm not going to write it out, but you'd replace the u's with x plus 5s. And don't forget the plus c, and you're done. The next topic is going to be the accumulation function. In this graph, as I keep going, more and more area accumulates under the graph. This can be written as the integral from 0 to x of f of t dt. This is the accumulation function. Notice that taking the derivative of the accumulation function gives f of x again. You might be given a graph of the accumulation function and asked a bunch of questions about it. Now let's talk about the fundamental theorem of calculus. It has two parts. We already talked about part 1, which says that the derivative of the accumulation function, so the derivative of the accumulation function is f of x. Part 2 says that for any integral from a to b of f of x dx, it's just going to be equal to f of b minus f of a. You don't need a plus c here, because for definite integrals, you do get a number and not a function as your answer. We already talked about rectilinear motion, but now let's revisit it after learning about integration. So knowing those two things, the integral of velocity is position. You might see it as x of t or s of t. And the integral of acceleration is velocity. The absolute value of velocity is speed. And distance is the integral of speed. Pretty straightforward. So if we were given a function and we were asked the average value of the function, the answer is rather simple. You just need the simple formula. The average value of a function f of x on the interval a to b is So the average value is going to be 1 over b minus a times the integral from a to b of f of x dx. If I call this average value f of c, then I can say that 1 over b minus a f of x dx equals f of c. Rearranging this gives me the integral being equal to f of c times b minus a. This is known as the mean value theorem. Moving on to solving definite integrals by u-substitution. The process is pretty much the same as before. We set x squared equal to u, and we end up with the integral of e to the u du. Now say we want to integrate this from x equals 1 to x equals 2. These current bounds are for x, right? So there's going to be two different ways to solve this. First, the way that I usually do it is just integrate this normally. So you'd get e to the x squared, and then you're going to evaluate that from 1 to 2 by plugging in these numbers. You're going to get e to the 4 minus e. And then another way to do it would be something called changing the bounds. So like I said, the 1 and the 2, these are the bounds for x. And I can also change it to get the bounds for u. How I do that is since I say that u is equal to x squared, I'd plug in the upper and lower bounds in for x. So I'd get the lower bound, if I plug in 1 for x, gives me an output of 1. And if I plug in 2 for x, I get 4. So if I plug it into here, and the 1 and the 4, these would be my new bounds. So that means I could have the integral from 1 to 4 of e to u du. And then when I integrate this, which gives me e to the u, since I already switched to the bounds to be for u, I can just simply evaluate this from 1 to 4. And notice it gives me the same answer of e to the 4th minus e. Now I'm just going to write the official format for this. So the integral from a to b of f of g of x. This is just the form of a function that can be integrated using u-substitution. This is equal to the integral from g of a to g of b f of u du. Use whichever way you want. This is just a little trick that might save you some time. Finally, another quick tip. If you're integrating an even continuous function like the one right here, which is where f of negative x equals f of x, integrating this from negative a to a is the same as 2 times the integral from 0 to a of f of x dx. And it's even better for an odd function, which is where f of negative x equals negative f of x. The integral from negative a to a of f of x dx is just 0, because you see here the two opposite things will cancel out. That's all for this unit. Don't forget to also look at the video for Riemann sums and the corresponding problem solving videos. See you next time, and goodbye for now.